Hi everyone, this is a work solutions video for Prac 15. We're first going to look at just 15a, which is your first reaction. So first up, you need a balanced chemical equation, which is what we've got here. If it isn't given to you in the question, you'd have to write one up, but that's your first step. The next thing you'd want to do is work out the limiting reagent, because the limiting reagent will determine how much heat you produce. So in this case, for instance, you've got 0.2 grams of magnesium combining with 30 mils of the 1 molar HCl. So we've got to first find moles. To do so, we need the molar mass of magnesium, and that's 24.31. We also need to convert our volume over here into liters because our concentration is in moles per liter. So our volume in liters is 0.03. If we're going from milliliters to liters, you divide by 1,000. The next thing we've got to do is find moles of both the magnesium and the HCl. In the case of magnesium, the number of moles is mass over molar mass. In this case, it's 0.20 over 24.31. That should give us a value of 8.22 times 10 to the minus 3. In the same way for HCl, my number of moles equals concentration times volume, which will give me 0.03. Now, based on this, I need to find out my limiting reactant. And what I can do is base myself on one substance and work out how much of the other substance I need using that. So for every 1 mole of magnesium, you need 2 HCl's. So I can say 8.22 times 10 to the negative 3 moles magnesium requires 8.22 times 10 to the negative 3 times 2 moles HCl, which is, in this case, 0.0164. That's how much HCl I need, right? But I've actually got 0.03. In other words, I've got more than what I need. So I could say that my HCl is in excess, and my magnesium is my limiting reactant. So excess HCl, limiting magnesium. That's your first step. You've got to figure out which of your two reactants is limiting. The next thing I need to do is use my MC delta T formula to work out how much heat is actually given off in this reaction. So my formula is MC delta T. This formula gives us the heat taken in or given off in this reaction. That is normally represented by the symbol Q, or we can also say delta H. Either way, it doesn't matter, but I'm just using Q to avoid a bit of confusion here. Now to do this calculation, we need to find delta T. Delta T is normally final minus initial, but as long as you're subtracting one from the other, you'll get delta T. In this case, it is 21.1, and that's 41.1 minus 20. And then we sub our values in. Now our mass for this case, we can either use 30 grams, because remember we had 30 mils of the acid. So 30 mils of acid is basically 30 grams of water, because the acid is primarily dissolved in water. We can also add the mass of the magnesium into it and make it 30.2. Either of those is fine. Both of them are inaccurate in some way. I'm just going to use 30 grams at the moment, just to make our life a little bit easier. But either of those would be acceptable. Finally, we need our C, which is specific heat capacity, and that in this case is 4.182 joules per gram per degree Celsius. Specific heat capacity tells you how much heat 1 gram would require to go up by 1 degree Celsius. And we're using the specific heat capacity of water here because we're assuming that the 30 grams is primarily water. Anyway, we plug all of this into our calculation. So this is us plugging all our values in. 30 times 4.182 times 21.1, that's MC and delta T respectively. When you calculate that out, you should get 2645.94 joules. Now, if we're converting joules to kilojoules, which is reasonable to do here because we've got a big number, what we've got to do is take our number and divide it by 1,000. And this should give you a value of 2.645 2.6594 kilojoules. Keep in many decimal places as you can up until the final answer. Alternatively, you can round off here to the appropriate number of sig figs, which is, in this case, that would be 2.64, and use the full number in your next step. The other thing to mention here is this reaction is exothermic, so what we really should do is put a negative into our expression. And we know it's exothermic because the temperature is going up. The system is losing heat and the surroundings are gaining some heat. So in proper sig figs with our units, and our sign appropriately is negative 2.64 kilojoules for this reaction. And finally, our last step is to find molar heat. Molar heat is basically finding total heat divided by number of moles. Molar anything is total divided by number of moles. So in this case, it's negative 2.64594 divided by 8.22 times 10 to the negative 3. Carry the negative over from the previous question, but as long as you have it in your final answer, that's the main thing. Also very important here is we're dividing by the moles of the limiting reactant, which previously we worked out to be magnesium. Think about why that is. There's a very important reason for doing that. When you solve this, you should get negative 321.6 kilojoules per mole, or in 3 sig figs, just negative 321 kilojoules per mole. So try repeating this calculation with your numbers. You should get something close to that. It wouldn't be too different, I don't think. Also try and do the calculations for the second experiment, which is the endothermic one if you can, and compare them to known values. Try and look the values up if you can, if you wanted to check how close or far you are. They'll never be exact, but it'll give you a good guide as to what you're aiming for. Thanks for listening.